calculation performed, voltage squared divided by power equals resistance, applies to direct current resistance. Incandescent light bulbs operate on alternating current, and their resistance varies with the frequency of the current. At 50 Hz, the resistance of a light bulb is generally lower than its direct current resistance. This is because the inductive reactance of the filament impedes the flow of current, effectively increasing the overall impedance. To accurately measure the alternating current resistance of a light bulb, an alternating current impedance meter is required. This instrument applies an alternating current voltage to the device and measures both the current and the phase angle between the voltage and the current. The alternating current resistance is then calculated using the formula resistance equals impedance times the cosine of the phase angle. In this formula, resistance is the alternating current resistance, impedance is the overall impedance of the circuit, and the phase angle is the angle between the voltage and current waveforms. If an alternating current impedance meter is unavailable, the alternating current resistance can be estimated by multiplying the direct current resistance by a factor ranging from 1.25 to 1.5. This multiplication provides a rough approximation of the alternating current resistance at 50 Hz. In the specific case, the calculated direct current resistance is 529 ohms. Multiplying this value by 1.25 yields an estimated alternating current resistance of 661.25 ohms. This estimated value remains significantly higher than the 39 ohms reading obtained from the digital multimeter. Several factors could account for this discrepancy. Firstly, the digital multimeter may not be accurate when measuring low resistances. Digital multimeters have internal limitations that can affect their accuracy at lower resistance ranges. Secondly, a light bulb being measured could be damaged or possess a different resistance than initially assumed. Physical damage to the filament or variations in manufacturing can alter the bulb's electrical characteristics. To elaborate further, it is crucial to understand the distinction between resistance, impedance, and reactance in alternating current circuits. Resistance is the opposition to current flow that dissipates energy in the form of heat. Impedance, on the other hand, is the total opposition to current flow in an alternating current circuit, encompassing both resistance and reactance. Reactance is the opposition to current flow caused by capacitance and inductance. Inductive reactance increases with frequency, while capacitive reactance decreases with frequency. In the case of an incandescent light bulb, the filament acts as a resistor and an inductor. The inductive reactance arises from the coiled shape of the filament, which creates a magnetic field when current flows through it. This inductive reactance opposes changes in current, contributing to the overall impedance of the bulb. The formula for inductive reactance is X sub L equals 2 times pi times frequency times inductance, where X sub L is the inductive reactance in ohms, pi is approximately 3.14159, frequency is the frequency of the alternating current in hertz, and inductance is the inductance of the coil in henries. The total impedance of the light bulb can be calculated using the formula Z equals the square root of resistance squared plus reactance squared, where Z is the impedance in ohms, resistance is the resistance in ohms, and reactance is the net reactance in ohms, which is the difference between inductive reactance and capacitive reactance. Since incandescent light bulbs primarily exhibit inductive reactance, the capacitive reactance is typically negligible. The power dissipated by the light bulb is given by the formula power equals voltage times current times the cosine of the phase angle, where power is the power in watts, voltage is the voltage in volts, current is the current in amps, and the cosine of the phase angle is the power factor. The power factor represents the fraction of the apparent power that is actually dissipated as real power. In a purely resistive circuit, the power factor is 1, and all the apparent power is dissipated as real power. However, in a circuit with reactance, the power factor is less than 1, and some of the apparent power is stored in the electric or magnetic field and returned to the source. The impedance of a circuit is related to the voltage and current by Ohm's law, which states that impedance equals voltage divided by current. This formula is analogous to the direct current version of Ohm's law, which states that resistance equals voltage divided by current. However, in alternating current circuits, it is essential to consider the impedance rather than just the resistance. When measuring the resistance of a light bulb with a digital multimeter, the meter applies a small direct current voltage to the bulb and measures the resulting current. The meter then calculates the resistance using Ohm's law. However, this measurement only reflects the direct current resistance of the bulb. It does not account for the inductive reactance that is present when the bulb is operating on alternating current. The direct current resistance of the filament is primarily determined by the material of the filament and its temperature. As the filament heats up, its resistance increases. This is because the increased temperature causes the atoms in the filament to vibrate more vigorously, making it more difficult for electrons to flow through the material. The relationship between temperature and resistance is described by the temperature coefficient of resistance. The temperature coefficient of resistance is a measure of how much the resistance of a material changes for each degree Celsius change in temperature. The temperature coefficient of resistance is positive for most metals, meaning that their resistance increases with temperature. In the case of an incandescent light bulb, the filament is typically made of tungsten, which has a relatively high temperature coefficient of resistance. As a result, the resistance of the filament increases significantly when the bulb is turned on and the filament heats up. The color temperature of the light emitted by the bulb is also related to the temperature of the filament. The higher the temperature of the filament, the bluer the light emitted by the bulb. The color temperature is measured in Kelvin. Incandescent light bulbs typically have a color temperature of around 2700 Kelvin, which corresponds to a warm, yellowish light. The efficiency of an incandescent light bulb is relatively low. Most of the electrical energy consumed by the bulb is converted into heat rather than light. The efficiency of an incandescent light bulb is typically around 5%. This means that only 5% of the electrical energy is converted into light, while the remaining 95% is converted into heat. Other types of light bulbs, such as compact fluorescent lamps, or CFLs, and light-emitting diodes, or LEDs, are much more efficient than incandescent light bulbs. CFL typically have an efficiency of around 25%, while LED can have an efficiency of up to 80%. As a result, CFL and LED consume much less energy than incandescent light bulbs for the same amount of light output. The lifespan of an incandescent light bulb is also relatively short. Incandescent light bulbs typically last for around 1000 hours. CFLs and LEDs, on the other hand, have much longer lifespans. CFL typically lasts for around 10,000 hours, while LED can last for up to 50,000 hours. The short lifespan of incandescent light bulbs is due to the fact that the filament gradually evaporates over time. As the filament evaporates, it becomes thinner and weaker, eventually leading to the bulb burning out. In summary, the discrepancy between the calculated direct current resistance and the measured resistance of an incandescent light bulb is due to the fact that the bulb operates on alternating current. The inductive reactance of the filament increases the overall impedance of the bulb, making the alternating current resistance higher than the direct current resistance. To accurately measure the alternating current resistance of a light bulb, an alternating current impedance meter is required. If an alternating current impedance meter is unavailable, the alternating current resistance can be estimated by multiplying the direct current resistance by a factor ranging from 1.25 to 1.5. Furthermore, the accuracy of the digital multimeter and the condition of the light bulb should be considered when interpreting the resistance measurement. It is also worth noting that the frequency of the alternating current supply affects the inductive reactance and, therefore, the impedance. In regions with a 50 Hz supply, such as Iraq, the inductive reactance will be different compared to regions with a 60 Hz supply, such as the United States. Therefore, the alternating current resistance of the light bulb will also be different depending on the frequency of the supply. The design of the light bulb filament also plays a role in its electrical characteristics. The length, thickness, and shape of the filament all affect its resistance and inductance. The filament is typically coiled to increase its length and therefore its resistance. The coiling also increases the inductance of the filament. The material of the filament also affects its electrical characteristics. Tungsten is a commonly used material for light bulb filaments because it has a high melting point and a relatively high resistance. Other materials, such as carbon and osmium, have also been used in light bulb filaments, but they are not as common as tungsten. The voltage rating of the light bulb also affects its resistance. A light bulb rated for 230 volts will have a different resistance than a light bulb rated for 120 volts. The power rating of the light bulb also affects its resistance. A 100-watt light bulb will have a different resistance than a 60-watt light bulb. The relationship between voltage, power, and resistance is given by the formula power equals voltage squared divided by resistance. This formula can be rearranged to solve for resistance. Resistance equals voltage squared divided by power. Therefore, for a given voltage, a higher power rating will result in a lower resistance. Conversely, for a given power rating, a higher voltage will result in a higher resistance. The type of digital multimeter used to measure the resistance can also affect the accuracy of the measurement. Some digital multimeters are more accurate than others, especially at low resistance ranges. It is important to use a digital multimeter that is properly calibrated and has a sufficient resolution for the measurement being made. The leads used to connect the digital multimeter to the light bulb can also affect the accuracy of the measurement. The leads should be short and have a low resistance. Long leads or leads with a high resistance can introduce errors into the measurement. The temperature of the light bulb can also affect the resistance measurement. The resistance of the filament increases as the temperature increases. Therefore, the resistance measurement should be made when the light bulb is at a stable temperature. The presence of other components in the circuit can also affect the resistance measurement. If the light bulb is connected to other components, such as a switch or a dimmer, these components can introduce errors into the measurement. The resistance measurement should be made with the light bulb isolated from other components. In conclusion, accurately measuring the resistance of an incandescent light bulb requires careful consideration of various factors, including the type of current, the frequency, the meter used, and the bulb's condition. Understanding these factors will help ensure a more precise and reliable measurement.